Hello everyone, this is Sion. Today, Sophia and I am going to present the SEMORec, a scalarized efficient multi-objective recommendation framework. This is a collaborative work with my co-authors at Apple. Let's begin with our motivation. In modern recommendation system, we have to balance multiple objectives. This includes not only maximizing the user satisfaction, but also achieving critical business goals and ensure the fairness in our recommendations. However, the current approach to multi-objective optimization faces several limitations. First, they offer limited human-in-the-loop intervention, making it difficult for the decision maker to integrate their preference or the business need. Second, many methods require the objective to be differentiable, which restrict the type of model and metrics that can be used. And third, many existing approaches are often computationally expensive, making them impractical to support frequent updates in dynamic settings. To build our framework, we first need to establish a common ground for all the objectives, because the raw objective value can be in very different scales. To make them comparable, we can apply min-max normalization to transform the objective values into a unified 0 to 1 scale. Once normalized, we can visualize each item as a point in a multi-objective space. Extending this, we can plot our entire catalog of items as a cloud of points. Each point represents a unique trade-off between the objective O1 and O2. Our goal is to find the best items within this complex landscape. Now let's use the background color to visualize the score distribution, where the lighter green indicates a higher score. On the left-hand side is a score distribution for the single objective optimization, only on O1. A high score is given to the items with a high O1 value, regardless what's the value for O2. On the right-hand side is a balanced score distribution for multi-objective optimization. Items are considered optimal only if they perform well on both objectives. Our scalarized framework is designed to find a uniform score that reflects this joint optimality. Handing over to Sophia to go over the details.
Hi, everyone. So now I'll talk about our approach. So in the first step of our approach, we focus on finding the items that are going to be eligible to be shown to the user. And these are the items that you see here in the red circle. These items are the Pareto front. That means that these items are improving both objectives, and you cannot improve one objective without hurting the other objective. In order to compute these points, we use a highly efficient algorithm called Kung's algorithm that runs in n log n time for less than 4 objectives, and n is the number of points in our solution space. Now, these items are the first items that we add to our recall set. However, in recommendation systems, we know that, especially if we're ranking multiple items, having very few items might lead to a stale experience or less of diversity. So we compute these items across different ranks in our Pareto front. So the red points would be rank 1, the purple points would be rank 2, blue would be rank 3, and then we can compute up to rank K, where K really depends on your application and how many points you want to show to the user. So now that we computed the recall set, let's identify how we're going to rank the items. How are we going to compute the score? So we have these adaptive scalarized objective function that takes the single objectives and it combines them into one single function. Let's break down this formula. So Fi is the value of the ith objective. Wi is the importance that we give to the ith objective. And our goal in this framework is to learn the W's, the weights, that will maximize this combined formula. Now here, Bi is a crucial parameter, and it's the bias of an objective I. And the reason why it's crucial is because in industrial settings, we've seen a lot that decision makers want to influence our short-term goals, depending on business goals. We also have lambda, which is a regularization coefficient that really influences how much the bias term will influence the final computation of the weights. So now let's see how we compute the W's. We compute the partial derivatives with respect to the different Wi's, and we come up with this closed form solution. The benefit of this is that it allows you to quickly adapt the weights and update them in a very straightforward and simple way. In this case, Fi is actually, Fi is computed as the aggregate of all of the values of items I over K. And what does that mean? It means that we're taking the summation for all the solutions that were defined by the Pareto front. We take their values, I, for objective I, and we sum all of their values. And then we divide by n, which is the total number of solutions in the Pareto front. And this is Fi. So this is how we combine our two approaches. We first compute the recall set, and then once we've computed the recall set, we really compute the weights that are optimizing the solutions in the Pareto front based on this formula. Now, coming up, let's talk more about the bias term. If the bias term is 0, we don't have any human-in-the-loop intervention. However, if we have the bias set into a value greater than 0, we see how this formula is updated. So let's talk a little bit about the experiments. So let's first take a look at this example of this actual experiment where we did not have human-in-the-loop intervention and the bias terms are set to 0. Our baseline in this case is a rank order optimized for objective O1. Our results we see great lifts here. These are online experiments. We see that both objectives achieve a high lift. But what we really surprised us is that we saw that the lift is on both objective O1 and objective O2, even though we're comparing against a baseline that is optimizing only for O1. Our hypothesis is that we achieve that because we're leveraging information of O2 that helps us escape local optima of objective O1. Now let's take a look at this case where we do have human-in-the-loop intervention, and our decision makers wanted to influence objective 1, such that objective 1 had 1/3 of the value of objective 2, or in other words, objective 2 is 3 times the weight of objective 1. So in this case, again, we have the same baseline that's optimized for objective 1, and we see even more pronounced lifts. We see that objective O2 is around 278%, and objective O1 is 123.3%. So this really confirms the efficiency of our framework, and we do see indeed that objective O2 achieves approximately 2.2 increase of objective O2 compared to objective O1. So this concludes our talk, and we're happy to take any questions.
I just have a question about the assumption about the independent between multiple objectives. Are they have to be independent, or it can be in a little bit more generic setting?
No, this is a great question. You know that in business, oftentimes it's a conflicting objective. It's actually one, optimizing for one reduces the other one, business versus relevance. So this actually is supporting any kind of relationship. It could be that they're correlated, or it could be that they're conflicted.
Thank you very much for the presentation. A question about when you talk about human in the loop, can you say a little bit more about it? It's obvious you can't say all of it, but to have a bit of an idea how this is helping and the effort that comes with human in the loop?
Yeah.
Sorry.
No worries. So there, in the general recommendations setting scenario, right, there are different stakeholders. There's product, then there are, let me put it simple, there are people that offer their items for recommendation, and then there are users. So in a scenario, there's a case where a stakeholder really wants to optimize one kind of objective that affects the business performance. And in that case, they could say, okay, for a short period, we really want to optimize for that objective. So can you help me do that? I want it to be approximately 3 times more than what another objective is. So they can give us that number, approximately how much they think it should be based on analytics and things, and then that is the input that you saw as a BI, bias term.
Hey, thanks for interesting talk. I'm not gonna pretend that I got all the math that is behind that, but I'm thinking my experience is that quite often the users don't really need the maximization of some of the objectives, but rather a certain level of it. Like, I don't want to maximize the diversity in proportion to accuracy, but rather maintain a certain level of diversity. Would your framework be able to handle these scenarios?
So that's a good question. So one thing that's not highlighted here is that this can be user personalized. So let's say you're a user that you really appreciate O1, and there's another user that appreciates O2, and there's a combination, right? So that formula, the summation, can be over the users as well. You can learn a weight at the user objective level, and that it's also dynamic, right? You can quickly compute those weights. So depending on what you want and what data you're giving us, we adapt the weights according to what you feel is the right, like that's more representative for your taste.
Yeah. Addition to that, actually, like you can plot the multi-objective graph at a different level, at the user level, at like store level, at whatever level. That can be optimized at that certain user or user group level.